Okay, so I wanted to do something really nice and simple with the Green's functions in order to counteract all the scary equations. So I did something, right? This is sort of the widest definition of dynamics that you can think of, and it's actually just equilibrium but frequency dependent, okay, which lets me make everything easier. So once again, I set up some parameters, and I'm going to do a Hubbard model. Okay, this time I'm going to have 50 sites, because it's essentially going to be at the cost of non-interacting. So I don't mind doing a bigger model. And I start by setting up a non-interacting Hamiltonian. So this is exactly the same thing you would see if I were doing the first thing that I showed you, the non-interacting code. And then I evaluate the Green's function. Okay, so this is the non-interacting Green's function. And if you stare at this code for a little bit, you will see that what it's saying is G equals, right, 1 over omega minus h plus I eta, where eta is some small number. Okay? Where once again, in a nice modern language, you will usually be able to do a matrix inverse in one row. Okay, so we can plot this thing. Okay, this is just plotting. And this is what the non-interacting Green's function looks like. Okay, so let's go back a little bit to my parameters. What do I have here? So it's non-interacting, so u doesn't matter. Okay, u didn't go into this calculation. Epsilon is minus u over 2, though. So if u is 10, then epsilon is at minus 5. I have T, the kinetic energy. Okay, so for tight binding 1D model, I'm going to have a bandwidth of 4T, right? And these other things don't really matter, right? Numerical parameters. So I have this weird shape. So what is this shape? Is this superconductivity? Who knows where this comes from?
1D dispersion.
Okay, 1D dispersion. How do I get it from that?
It's 1/2 singularities.
Sorry?
Is it 1/2 singularities?
You could say that, yeah. But again, it's just, this comes just from the 1D dispersion relation. So what is the dispersion relation of a 1D chain? You guys know this? Yeah, exactly. It's just 2T times cosine of something like this, right? This is what you saw in tight binding. Okay, so here this will translate into something like I with some number. So if your dispersion is a cosine, right, then your density of states, which is essentially the spectral function here. Okay, so you should know this from your solid state textbooks, should be something like 1 over d omega of k to dk, right? At k equals k of omega, something like this. So you have to take a derivative of this thing, right? So, you know, what happens is that at the edges, the derivative will diverge. 1 over the derivative will diverge. And you're going to get a shape which diverges here, goes down to something finite here, and looks like this. And then outside the band, you will just get nothing. Okay, so that's just what this shape is. This is totally non-interacting physics. It has nothing to do with superconductivity or something like this. So as James said, don't be misled by spectral functions. They can mean anything. One thing we can say about this is that if you look at my model, the Hubbard model that I actually wanted to solve, okay, I hope some of you know that if I set u to, right, epsilon to minus u over 2, I should be at the particle hole symmetric point. Okay, so particle and hole excitations should be the same. Or in other words, that means that the spectral function should be symmetric around 0. But it's not. It's symmetric around this point, okay, which is just epsilon. Okay, and it has this width of 4t around that. Okay, so this is due to the fact that I don't have the interaction. Okay, the interaction hasn't figured into this calculation at all. Okay, so now let's do some perturbation theory. Okay, so I want to calculate an interacting Green's function, big G. Okay, I'll define a Fermi function here, which I don't actually use, never mind. And then I plot the non-interacting spectral function again. And then I stick in a self-energy. Okay, so I set this up so that I can do an iterative calculation with the self-energy that's a functional of G. But I didn't actually do this. I'm doing just one iteration. And I'm going to sort of guess my self-energy. Okay, or stick in a self-energy that I think is correct. Okay, which is actually what theorists do quite often. Okay, so my self-energy should be this heart rate bubble. Okay, and what this actually is U. Okay, so it's a vertex. It comes with a U, and then it has a G at 2 equal times. Okay, and there is some rule I didn't go into, but you have to take one of them to be infinitesimally bigger than the other. Okay. Now what you can show is that this thing turns out to be actually the occupation at the chemical potential for this model. Okay, so I can replace this G, which is this thick line, with just an occupation at the chemical potential. Since I set up the model to be F occupied, then that's going to be 0.5. Okay, so this is the self-energy that I guessed here, just U times 1/2. Okay, and let's see what that gives us. So how do I use this? My interacting Green's function is just, okay, what does this say? So again, we had G equals 1 over omega minus H plus I eta. Big G is 1 over omega minus H plus I eta minus sigma. Okay, sigma in general can be a matrix, can be frequency dependent. In our case, it's frequency independent, and if it's a matrix, and it's a diagonal matrix. Okay, so I just use that. I stick that in here. Then I calculate my spectral function using that guy. And here's what I get. Okay, so the blue is what we saw before. It's the non-interacting spectral function. And when I do this perturbation theory, I get my interacting spectral function, which, okay, you can see one thing is nice about it. It's at least particle hole symmetric. So by guessing this self-energy, I solved that problem. But it's essentially just shifted in energy to the right point. Okay, so in a way, what I've done with this self-energy is remove the epsilon. Okay, so this is not so interesting. But I can say for a moment, hold on. So I know that a Hubbard model with a big U, actually this is going to end up being an antiferromagnet, right? So what I should really be doing is putting say the odd sites at spin up and the even sites at spin down. This would sort of be a better guess for my occupation, at least for very large U. So we can guess that as our self-energy. Okay, and that's this line over here. So if I change to that self-energy and rerun this thing, then I have suddenly a Mott insulator. Okay, I have a gap. It has that distinct superconductor look, though it isn't a superconductor. And the gap is actually, right, this should be just about the right Mott gap. Okay, so I want you to take two things from this calculation. And once again, I will give you this code to play with. Number one, okay, despite all the big equations, this is super easy. Okay, you calculate a non-interacting Green's function. This is just essentially diagonalizing a matrix and inverting another matrix. Then you stick in a self-energy, okay? In our case, I guess the self-energy. In general, the self-energy is going to be some functional of your Green's function or your non-interacting Green's function, depending on the approximation that you make. But this is going to be something relatively trivial. You might have to iterate to do this, but this is really something that's super simple to program. And once again, you can usually do it in Python quite easily. Okay, that's number one. Okay, so remember, Green's function is not so hard, actually. Okay. Number two, if I do this, and if yeah, you can see that by playing a little bit with self-energies and rather convincing arguments, I can show you whatever I want. Okay? So I should not be trusted with this technology. Okay? So no one really should. And a lot of theory, when people tell you, oh, this is the self-energy that solves this problem, so there we have a reliable solution for this, that essentially means that they knew that if they used this self-energy, they would get the result that they expect, and they are showing you what you want to see or what they want to show you. Okay, so you should be very careful about this stuff. Okay, it's very easy to come up with self-energies. It's very easy to come up with self-energies that will give you what you want, and that's not how you should do science. Okay, so you should give this some thought before you actually do any sort of calculation for this. So the last thing I want to do during the remaining time is to show you how we do dynamics with Monte Carlo. And I'm going to do that using a different expansion, okay, which also has diagrammatics. It's a propagator expansion. It's not quite a Green's function expansion, but this is sort of similar. So up to now, everything we've been doing is lattice models. Now I'm doing an impurity model. Okay, so this is the same Anderson impurity model that James talked about. And we're going to talk about an impurity solver. Okay, so when I'm doing an impurity solver, I have a lot more freedom in terms of the methods I use than when I do a lattice solver, because the impurity, which is the interacting part of the system, is small. So what I can do is I can exactly diagonalize the impurity. And then in a Green's function type method, I can also exactly diagonalize the infinite but non-interacting bath. Okay, and this is the thing that you can't do in a wave function method. This is where Green's function methods really shine. And this is one of the main reasons why sort of the dominant methods for DMFT are these quantum Monte Carlo Green's function methods, even though they have to be formulated in imaginary time and they have stochastic errors and all these disadvantages. So what I'm going to be doing is called the hybridization expansion. And the way it works is I divide my system into an impurity subspace. Okay, so I have a local subspace, which is like a single side of a Hubbard model. Okay, so sum over sigma and sigma epsilon plus u and up and down. I have a bath part, which is sum over k, epsilon k and k. And I have a hybridization part, okay, or a dot bath part, which is like sum over k. Yeah, this also has a sigma of, okay, so this is going to be a dagger k d sigma plus Hermitian conjugate. Okay, so the idea here is that A's are bath operators and D's are dot operators. Everyone is fermions. Okay, so this is called an Anderson impurity model. Okay, so what I'm going to do is I'm going to do perturbation theory in the hybridization. Okay, now that means my reference system, my H0 is not non-interacting because it has this term in it, but it's divided into two completely separate parts. There's an impurity part, which is interacting, but it's small. It's only a single site. Okay, so it's 4 by 4. I can easily exactly diagonalize it. And there's a bath part, which is essentially infinite, but it's also non-interacting. So I can solve it semi-analytically or solve it with some lattice solver, which is very efficient. I can make it as big as I want. Okay? As soon as I add this, I have an infinite many-body system. Okay? So the impurity model is still, difficult, but because interactions are localized, and the difficulty is somewhat easier. Okay. So now I'm going to do the whole process that I talked about before with diagrams, but instead of my vertices being interaction vertices, my vertices are going to be something where an electron goes between the dot and the bath. Okay, so it's a hopping vertex. So I have an object like this, which is now called a propagator. It's not quite a Green's function because, because my H0 is interacting, I cannot quite work with Green's functions. I have to work with objects which have the Hilbert space dimension of the impurity. Okay, so this has many body indices, alpha and beta, which are like the dimensions of the Hilbert space of the impurity. And I can write this thing in terms of a bare propagator. Okay, so this is an interacting propagator, but it essentially tells you what happens when an electron is propagated on the dot without coupling to the impurity. Okay, so that means if I've exactly diagonalized the dot subspace, then this is going to be something like e2 minus e alpha times time, where alpha is the energy of a state. Okay, and again, I found those by diagonalizing a 4x4 matrix, which actually is already diagonal to begin with in this case. Okay, so you can just read the 4 possible values of E alpha from that first equation. Okay, and then my perturbations, okay, and again, these are time, okay? These lines are time. So I have a vertex which is like this. Okay, if I want, I can put a little arrow on it, but I'm not going to. And this describes an electron going between the dot and the bath, okay? So you have a d dagger times an AK. And I'm going to be able to analytically sum over all these k's. Okay, so essentially I'm doing everything in the dot subspace. So if I have an 8K somewhere, right, bath annihilation operator, I must have somewhere else something like this, A dagger KD. Right? Every A dagger K has to be traced out with an AK, otherwise I'll get 0. Remember Wick's theorem from before. So because the bath is non-interacting, I can use Wick's theorem for bath operators. So there's a factorial number of permutations of bath operators that appears here, and I can sum them up as a determinant, things like this. But, well, more importantly, these lines have to be connected to each other. Okay, so the diagram rules here are draw lines like this. Okay, they're called hybridization lines. Each line has to connect at 2 points. Okay, and these are somewhat simplified version of the diagrams that go into the full model. You can do this in several levels of detail, but I want to do the minimal amount of detail that one could possibly do. Okay, so so essentially now I can look at this thing and I can sum up all the diagrams that appear here. They look a little bit different than Green's functions diagrams, but they are diagrams all the same. Okay, I want to show a few examples, which is why I'm doing a few. And then I can formulate a Monte Carlo algorithm around it. So how does the Monte Carlo algorithm work? I start from, say, an empty diagram, a bare propagator, and then I can have Monte Carlo moves which add and remove hybridization lines. Okay, and as I do this, I'll randomly walk across this infinite space of possible diagrams that exist and sum them all up one by one. Okay, and if I sample enough diagrams and if I did this right, then hopefully I can evaluate this thing, which is the sum over the whole set, the infinite set of diagrams. Okay. Now there are a few special issues and caveats here that one should worry about. One is, as I said, you have Wick's theorem. So if I actually have a particular set of vertices, okay, I sort of have to worry about two types of vertices. Let's call them black and white vertices, right? But essentially they're like A's and A daggers. So I can only connect an A to an A dagger and vice versa. So for something like this, right, I have to have the same number of A's and A daggers, okay? And in this case, I can only connect one line here. In this case, I can do it like this, or I can do it like this. Okay? And it turns out that because of fermion commutations, this one will have a minus sign. Okay? In general, for a diagram with 2n vertices, n of which are A's and n of which are A daggers, I'm going to have n factorial, for 2n vertices, I have n factorial diagrams that come out of all the possible permutations of these indices. Okay? Now, if I'm summing all of them, then at least in some of the literature, this is called path integral Monte Carlo. Okay, your configuration space that you're summing over isn't actually diagrams. It's not diagrammatic Monte Carlo. It's actually these, right? It's these objects. Okay, you never have to draw the diagrams. You just calculate the determinant that is given by these objects. So that can be very efficient. Okay, let's leave that aside for a moment. What I can also do is just evaluate diagrams one by one, but then I would get an extra sign problem that has to do with, with these fermionic minus signs. So it's substantially better to use this sort of symmetry and evaluate that determinant, right? So again, I get n factorial diagrams and n to the third time out of this. Pays off a lot. Nevertheless, I will show you that we will not do that, and we will actually get something better. Okay, and we'll see that in a couple of ways, actually. Okay, so essentially, this allows me to calculate a propagator. Okay, a propagator is an object like this. Okay, this object in itself is not of great interest physically. Okay, what you want is to calculate maybe Green's functions or maybe time-dependent observables. This does not quite give you that. Okay, so you have to assemble out of propagators the objects that you actually want. Okay, and this is where the Keldysh contour comes in. So the way that you do this for an actual calculation for something physical is that you work on a contour like this. You have some observable here, okay? And then your interaction vertices live on this contour. And then I can have hybridization lines like this for this particular configuration. But it's important to remember that I can also have hybridization lines like this. Okay, cross-contour hybridization lines. Okay, and when one writes a code like this, then you actually have to take care of all this bookkeeping, see which branch you are, and work out all these vertices, and all the diagrams actually live on this complex contour. Okay. Now, what does this actually describe? Okay, so what happens here is that here I have something like eta minus IHT. Here I have my operator. And here I have E2 plus IHT. Okay, and again, these pluses and minuses are going to go into my vertices. And then I'm taking this whole thing and applying a trace. Okay, so I have some rho here, which is my initial condition. Let's call it rho 0. and I'm applying a trace to this whole thing. So this whole thing, once you sum up all the diagrams, translates into something like this. Okay, so this is actually what we want. This is like the time-dependent value of A. And we have to take care of the fact that my Dyson expansions of these guys are going to drop operators before and after my operator. Okay? So again, everything is exactly the same as before. It's, now you can think about what happens when you actually want to calculate Green's functions. So Green's functions are not just an operator at the tip of the contour. They're two operators at two different points. Okay, so for a Green's function diagram, you will have maybe in like a D here at time t, and then you have a D dagger at time t prime. Okay. Now you also have, right, and let's draw these as red vertices because they're special. Okay, we'll make one of them white and one of them black. Full and empty, right? In addition to these, we have a bunch of regular vertices, right? So let's put a few of those in. Okay, now what happens is that these things can be connected among themselves, but the two special vertices are not connected by a hybridization line. They're not connected to any other vertex because they're just a D or D dagger. They're not a D dagger AK. Okay, so they don't come with a bath operator. They're only a dot operator. So these vertices are a little bit different than all the other vertices. And again, when you write your code, you have to pay attention to these differences and do everything correctly. Okay. There's one more aspect I should talk about that goes into this. Okay, so we said that that these lines actually have a state. Okay, these are not like Green's function lines in the standard expansion. They represent time, but at any point during this time, your dot is in a particular state. Okay, so as I go along time, and here it doesn't really matter if it's a Keldysh contour time or not, I have the four possible states of the dot, okay, which I can represent as follows. Okay, so you can think of this as a dotted line means a spin orbital is unoccupied, and a solid line means that it's occupied. And then my vertices change the occupation of a particular line because they all have either a D or a D dagger. So actually, the way that my diagram looks in the detailed view is that I start, for instance, unoccupied. And then if I have a vertex here and here, then I change the occupation of one of my spin states in between. And if I have another one here, then I'm changing the occupation of the other spin state. And then I have to look at all these places, and in each one I'm in a particular many-body state on the dot. So here I'm in state 0, up, up, down, down, and 0 again. And each one of these is associated with an energy and with a local propagator. Okay, and as you propagate, you have to maintain all these things. These are all matrix elements of some tensor object. Okay. But essentially, this is it. Okay, this is everything that goes into a hybridization expansion. Unfortunately, this is not something that I can do in 100 lines of Python code. Okay, this really is a a large code project. But again, if you want to see a code like this and how it's constructed, you can come to me and I'll show you. And there are several high-quality codes of this sort available online. So James mentioned Alps and Tricks. These are very popular ones. There are a few others also. Okay, so this is a hybridization expansion. Okay, most of what I said is not specific to the Keldysh contour. Okay, so you can do this in Matsubara time. And then you have a single contour. And we've also done it in a mixed solver. That's right. What is the point of something like this? So if you want to start in an interacting initial condition, right, an equilibrium interacting initial condition, for instance, equilibrium for a non-zero u, and then you want to do some sort of quench from there. So say you want to start in equilibrium for a finite u, and then turn off u and see what happens, or make u bigger and see what happens, or suddenly activate a voltage. Then you can do that by starting from here. Okay, and again, the annoying thing about this is that you have 3 branches on your contour, and things act differently between them, and you have hybridization lines between all of these guys going back and forth. Okay, so in terms of bookkeeping, it's more complicated. Conceptually, it's the same. Okay, so that's the basic introduction of what the hybridization expansion is. Are you guys with me up until now? Yeah.
How harder is to work with Hamiltonians which do not preserve number of particles?
So let me think what people have done. Well, for small impurities, you can certainly do it. In general, people have not done that much of it. Well, at least people have worked with Hamiltonians that don't preserve spin, things like that. You want Hamiltonians that don't preserve the total number of fermions? No. I don't think someone has thought about that. But we've worked with mixed fermion boson Hamiltonians, for instance, so the number of bosons is not conserved.
Well, if I want to look at condensate, then probably I need an impurity.
Well, a condensate is bosons, so yeah, we can do bosons. So, like one model for which this expansion works quite well is an Anderson-Holstein model. So you have one fermionic impurity coupled to a boson bath. Okay, a non-interacting boson bath. And if you want to have a condensate, right, a condensate is non-interacting physics. You can totally do that. Okay. And essentially, right, what's nice about this sort of method compared to exact diagonalization, DMRG, things like this, is that baths are free. So you can have multiple fermion baths, multiple boson baths, multiple fermion and boson baths. All these things are very easy, relatively, to add. They don't cost you anything. Actually, the more baths you have, the more dissipation you have. So the algorithm actually becomes a little bit better. Okay, so in many ways, this is very complementary to the methods that I was talking about in the first part of the course, because it breaks down in totally different ways. So okay. So given that we have this, okay, this is one of the most successful algorithms for doing DMFT. Okay, so if you want to do DMFT in equilibrium for strong interactions, which is usually where you do want to do DMFT, otherwise, you're not using it, then at least for small impurities, if you don't need to do large clusters and things like this, then this is the method of choice. Okay, so people use this a lot. People use it for multi-orbital systems a little bit. But we're talking about equilibrium here. Okay, so everything is done on the Matsubara contour, the imaginary time contour. And then what you would really like to do if you're interested in dynamics and spectral functions and quench physics and thermalization, all these things that some of us care about, is do this in Keldysh. And in Keldysh, it's a little different. Okay, so what happens is that the way that Monte Carlo methods break down is known as the sign problem, which James has mentioned. And there's no one sign problem. There are many sign problems, some of which are more severe than others. The most famous sign problem is the fermionic sign problem, okay, which tells you that if you try to do quantum Monte Carlo for a generic system, at least with many fermions, then as you make the system bigger or as you make temperature lower, then your signal to noise ratio is going, right, for a given amount of computer time, is going to decrease exponentially. Okay, so eventually, you know, you have that exponent just like in exact diagonalization, but it appears at a different point, and there are different things you can do before that exponent kills you. Okay, that's the idea. So you're still eventually limited. And the fermionic sign problem is thought to be a very basic thing. Okay, it's thought to be connected to NP completeness, and it's not something that most people believe is solvable. Okay, we don't think that we can actually, like, in general, solve the fermionic sign problem, because if we could, then we could solve some spin system which could be mapped onto an NP-hard problem. Okay, but that again doesn't tell us anything about solving it for particular systems. So, am I posing for a picture, or am I? What's? Okay. So. Okay. So it may be that essentially all systems that we're interested in physics have, you know, in some phrasing of permutation theory, and quantum Monte Carlo have a weak sign problem. Okay. So there's a different sign problem that appears when we do dynamics, which people have for many years argued about whether it's something which is as basic as the fermionic sign problem, or something which is more specific to the way that we do the problems. And there have been a few, you know, a few cases where people have bypassed it, but not anything really general. And we don't know the answer yet. But this dynamical sign problem that appears in real-time propagation essentially means that as you're summing up all your diagrams, okay, you get factors like this in an imaginary time expansion. Okay, so all your diagrams have a lot of factors, right, which look like exponents. And these are fine. You also have plus or minus ones, which are less fine. Okay, these are what causes the fermionic sign problem. And this you don't have for bosons. But if you try to go to real time, then you get factors which look like this. Okay, so you get complex exponents instead of real exponents. And these are some sort of, you know, vectors in a complex space. So these give you more signs or more complex phases. And as you try to sum up a lot of essentially random phased complex numbers, you will get garbage very quickly. Okay, so you have to sum up, right, that there are cancellations between these. There are pairs of diagrams that if you sum both of them exactly, then they will sum up to 0. But if in your stochastic algorithm you only summed one of them, then you're going to see that random phase somewhere in your result. Okay, so it causes more of a sign problem than you get when you do imaginary time. And essentially the way that sign problem looks is that it's in time. Okay, so what does a sign problem look like? Okay, let's see a sign problem in time. I'm evaluating some property of the system. Okay, so I don't know, the magnetization that we looked like on our site. Okay, and it looks like this. If I try to calculate this with quantum Monte Carlo, then I'm going to get the right answer within some noise. Then my noise will grow. Then I will get absolute garbage. Okay? So then I know something is wrong. If I want to actually analyze this, I have to look at the error of this thing, right, on a logarithmic scale as a function of time. And what I will find is that it grows exponentially. Okay? So my noise to signal ratio, essentially, as a function of time, grows exponentially. And that's how I know I have a sign problem. Okay? Sign problems are exponents in the difficulty of solving this problem. Okay? Okay, so when people first did this, this hybridization expansion and many other kinds of quantum Monte Carlo in real time, they came across this, yeah, in a bit, and essentially they saw that this happens. They said, okay, this is terrible, this is useless, and then they went to imaginary time. Okay, and there they have stayed ever since. So, you know, even when you want a spectral function and you have to do this analytical continuation with maximum entropy, which people know doesn't always work, you do it in imaginary time because it means you don't have to deal with this sign problem. Okay, and exponents are bad. You don't want exponents in your calculation. So, so what I'm going to talk about in this last talk is what, you know, some work that we did on trying to fight this dynamical sign problem so that we can try to do Monte Carlo in real time. So we have a dynamical sign problem here, okay, and I want to talk about how we've approached it. The idea is that you would like a more efficient way to sum up these diagrams so that you don't need to sum up so many at long times. Okay, as time increases, right, your contour is bigger, the number of diagrams that contributes gets bigger, and eventually you have to sum up an exponential number of diagrams in order to get a correct answer, and that's when the sign problem starts showing up. And you would like to mitigate that as far as you can. So I will show you a couple of things, right? The first one is going to be right, a little bit for teaching purposes, because it has to do with these self-energies that we talked about. And this, okay, so the old method, the method which clearly has a sign problem, we call the bare expansion. Okay, and this is essentially, I take my propagator or my modified propagator, which contains an operator, Green's function, whatever I want, and I sum it up, brute force, okay, diagram by diagram like this using Monte Carlo. Okay, and eventually, as my time gets longer, this explodes. Okay. You can do something a little bit smarter, and this was done by Emmanuel Gould, whose name kept popping up on James's slides, which is called bold line, okay, QMC. Okay, so what's a bold line? A bold line is, right, this is a thin line. Okay, this is a full Green's function. You can also define an, you know, a slightly full Green's function, which is not very full. Okay, this is why I'm used to drawing this as extremely big. Okay, so we can tell the difference. This is the result of using some self-energy. Okay, so we will define this as the solution of an integral equation that looks like this. Bare propagator plus, okay, time integral over these 2 points, something like this. Okay. You can see that this has the form of a Dyson equation, like we saw before, even though, again, this is not quite a Green's function and everything is sort of subtly different, but right, essentially the structure is the same. This object is called a self-energy. Okay, it's a self-energy for an approximation called the non-crossing approximation. And you should be able to easily convince yourself, this is a nice exercise to do, that this sums up all diagrams where, big surprise, the hybridization lines do not cross each other. Okay, so you have diagrams like this, which are called rainbow diagrams, diagrams which have a large number of things like that. Okay, all diagrams of this form. So again, it's an infinite subset of all the diagrams that appear in the expansion. Okay, the hybridization lines do not cross each other. Why is that a good thing to sum? Why is that a good approximation? Can anyone tell me? What's the physical motivation for summing only diagrams where the lines don't cross? Okay, there isn't any. Okay, we do this because it's mathematically easy. Okay, this is a simple self-energy that works. Okay, so it's not right. I've heard. I think it was Emmanuel who calls this the never correct approximation. Okay, so all of these self-energy things are somehow cheating. Okay, but they do something. Okay, so we have defined this set of bold propagators. Okay, what we can do now, we still, right, we don't like guessing self-energies, right? We want an exact solution. So how do I keep losing that thing? So we would still like to do Monte Carlo and sum up all possible diagrams, but we would like to take advantage of the fact that we can quite efficiently calculate this bold line. Okay? So what we can do now is write an expression for the full propagator in terms of the bold lines. Okay, so the first order term in this expansion is already all non-crossing diagrams. Okay, so at first order we already have an infinite number of contributions from the Baire series. And then, in order to avoid double counting, okay, so what do I mean by that? If I sum up a diagram like this, then I'm going to be counting some non-crossing diagrams twice. Okay? So it turns out that you have to sum up all diagrams where every inclusion, okay, an inclusion is a set of hybridization lines that cross each other, has at least one crossing. Okay, so you have to sum up diagrams like this, and you have to sum up diagrams like this. Okay, but you do not have to sum up diagrams like this, and you do not have to sum up diagrams like this, because each one of these diagrams has a one crossing inclusion. Okay, and if you do this, you will get something like that. Okay, this is supposed to be a straight line. Okay, imagine this is a straight line. So you will get a decrease in the sign problem, but you will still get a sign problem. Okay, so this is nice, this helps, this lets you go to longer times before the sign problem kills you, but it doesn't quite solve the problem. Okay, so we need something a little bit better than this. And this is what Inchworm Monte Carlo is. So Inchworm Monte Carlo is sort of like taking this idea to the absolute extreme, to infinite order. Okay? And the idea behind that is that we think that the diagrams, or at least one set of diagrams that we are quite certain is causing an exponential sign problem, is improper diagrams. Okay, they're related to the set of improper diagrams that we had in the previous expansion. So what do I mean by improper diagrams? One contribution to this guy in the Baire expansion is diagrams like this. Okay, where I can remove any one of these inclusions. Okay, so if there's like, there turns out to be like a typical length and a typical distance between these guys that they like being at, and I can remove any one of them. So if my time grows linearly, then I have up to n inclusions like this, right? And that means I have 2 to the n diagrams with all possible ways of adding or removing any one of these inclusions. So you sort of see trivially an exponent popping out of that. But actually, all of these diagrams are summed up with the non-crossing approximation, with the bold line Monte Carlo. Okay, so they should be completely removed by that. So why do I still have a sign problem? Well, if I look at this bold line expansion, okay, my full propagator is written in terms of, okay, this is supposed to be a bold line, okay, but it has contributions that look like this. They might be a little bit further apart, but there's still a sense, right, a sequence of these trivial one crossing inclusions. And these could be actually contained within a one crossing self-energy. Okay, so I could do a higher order self-energy and remove those, but then I would still have a sign problem because of the things which are just one order higher. Okay, so this, any sort of approach like this will still have something one order higher, which will produce eventually an exponential sign problem. Okay, so we really have to do something that will remove that. Okay, and that's what happens in Inchworm. Okay, we do something different. Okay, so the idea is that doing this is exponentially hard at long times, but it's also exponentially easy at short times. So can we take advantage of the fact that it's very easy to sum up short time propagators in order to make it easier to sum up longer time propagators? Okay, so in order to do that, okay, again, this goes back to a little bit to what I did with matrix product states, right? Suppose that I have solved, right? Believe me that I have solved some small problem. Can I use the answer to that small problem to solve a slightly bigger problem? Okay, so the small problem that I would like you to assume for a moment that I've solved, okay, is suppose that I have calculated, right, every propagator is between 2 time points on the contour, right? I draw them with some length, but in principle, they live on the contour, and you know, propagators are between here and here, or between here and here, doesn't matter. Okay, so when I draw this, I actually mean that I will need all sorts of propagators at lengths in between these endpoints. So suppose for a moment that you believe me that I have somehow obtained every possible propagator that starts from the beginning of time, okay, of my time contour, and ends no further right than this arrow. Okay? So I'm going to write an expansion that uses those propagators in order to evaluate this full propagator until the end of my contour. So what's the first term in that expansion? It's just going to be this, right? So what that contains is every possible hybridization line that begins and ends to the left of the arrow. Okay? But it doesn't have any hybridization lines to the right of the arrow, for example. So this is not the right solution. This is just some sort of approximation. But you see that already at this order, it's sort of very powerful. It has a lot of diagrams in it. Okay, so what do I have to add in order to make this exact? Well, clearly I can have whatever diagram I want to the right of the arrow, right? Because I haven't summed any diagrams here. Okay, so anything there is fine. And I'm going to have an exponential sign problem here. But what I can do is I can keep this area to the right of the arrow small. Okay, so what this is doing is sort of increasing my contour length. So I'll increase it by small steps at every point, and then hopefully, right, this won't get exponential. But that's not enough, right? So if I sum up this and all diagrams here, I'll have all hybridization lines beginning and ending to the left of the arrow, and all hybridization lines beginning and ending to the right of the arrow. Right? But there could also be hybridization lines beginning here and ending here. Okay? So I have to add things like that. So I will need terms that look like this. And then what it turns out is that, you know, here at the end of a hybridization line I have an operator. right? I'm changing the state of my contour, as I showed you before. So I have to cut this propagator. These are two different propagators, actually. So once I cut it, here I have all hybridization lines from here to here. And here I have all hybridization lines from here to here. But I no longer have here hybridization lines coming from here to here. Okay, so I'm going to need to add more diagrams. Okay, so I will also need diagrams of this form. Okay, and when I add those, I'm going to have to cut the contour again. Okay, so you can continue this, but essentially you can come up with an exact, right, a formally exact relation for which diagrams need to be summed up in this expansion and which ones don't. Right? For example, if I add any line here, you can see that that would be double counted because this propagator already includes all hybridization lines that started in here. Right? So there's a simple rule. Okay? Right. I will say it in words, and then we'll look at some examples. Okay? A diagram that we sum is called Inchworm proper. Okay? A diagram is Inchworm proper if it is composed only of sets of hybridization lines connected by crossing, which have at least one endpoint to the right of the arrow. Okay, so that was a really clunky sentence, okay? But let's do some examples, okay? So here it has some hybridization lines, okay? All of them have some endpoint to the right of the arrow, so this is fine. Okay, well, this is supposed to be a check. Here I have one hybridization line, and it has an endpoint to the right of the arrow, so it's fine. Okay, this is Inchworm proper. Here I have two hybridization lines. One of them has an endpoint to the right of the arrow, one of them doesn't, but these two are connected by crossing. Okay, so they're in a cluster of connected diagrams. Okay, so this is also fine. Okay, so let's do an exercise. Is this one Inchworm proper or not? Okay, we got both answers, so one of them has to be correct. Okay, let's see. How many clusters of connected clusters of hybridization lines are there here? Okay, two, right? So let's paint them. This is a cluster. These two are crossing. And this is a cluster. Okay? Each one of these clusters has an endpoint to the right of the arrow, right? So this is Inchworm proper. Okay, what happens if I add this? Is it still Inchworm proper? No. Okay, good. How about if I add this? Okay, James wants us to finish early, so yeah. Okay, good. So you see, it's a simple rule. Okay, you can write a little graph theory algorithm that will tell you whether a particular diagram is good or bad, and you can sum up all these diagrams. Okay, once you have this rule, this works out into an algorithm. Okay, so what is the algorithm? This is called, we call it inching. Okay, so you start by making some very short propagators, and then you use this Inchworm step to make some slightly longer propagators, and then you do that again to make slightly longer propagators, and you continue doing that until you get to however long you want. Okay, and the question is whether this will actually do something to the sign problem. Okay, so we can sort of think about it in these terms. Okay, in a way, in order to have an exponential sign problem, I have to have something going all the way from the beginning to the end of the contour, like these guys. Okay, I have to have important contributions which sort of grow in number exponentially with the length of the contour. In both of these things we have it. But what happens in Inchworm? So suppose I have a very long Inchworm diagram. Okay, so the way that looks, okay, I'm just going to remove this one so I have some extra room. Okay, so it looks like this. Okay, and I want to find something that goes all the way to the beginning of the contour, and it has to be Inchworm proper. Okay? So I can really only do that in two ways. Either I have a really, really long hybridization line. Okay, these are normally suppressed, right? At long times, these things are usually suppressed. But also, combinatorially, there is one of these. Okay? So that's not so bad. Or I have to have a daisy chain like this. Okay, so this is a really high order contribution. Okay, but it goes all the way to the beginning. Now, the difference between this guy and this guy is that here I could remove any one of these. Okay, so there is an exponential number of these guys. There's 2 to the n of these guys. But there is one of these guys. If I remove one of these daisy chain elements, then the whole thing is no longer Inchworm proper. I have a disconnected cluster. Okay, so combinatorially, the number of diagrams that I have to solve, that I have to sum up, is much smaller. Okay, the diagrams, right, the growth of diagrams with the length of the contour looks like it might be linear or something like this, but it's not. It doesn't seem like it should be exponential. Okay, and of course, if I do have a lot of diagrams of this form to sum up, then eventually the method will collapse. So one has to go and try. So when we try this, we typically get something that looks like this. Okay, so it either plateaus or gives you a power law, but it doesn't, it's sub-exponential. Okay, so this seems, at least in a lot of cases, not in all cases, but in a surprising variety of cases. And we've done this for several models, for several different expansions by now. This is just the first example. It seems to remove this exponential sign problem for impurity models. Okay, so now we can actually do, for impurity models, we can do real-time dynamics. And that means that by now we've done DMFT in real time. We've done a lot of things, and it's progressing very slowly. It's much, much more expensive than doing imaginary time. Okay, we're not even close. So a problem that can be done on a desktop basically needs a supercomputer to solve. But we sort of win in terms of scaling. Okay, so in order to get better, say, frequency resolution with imaginary time, you need exponentially more power because of the problems of analytical continuation. And we need polynomially more power. Okay, so for, say, big enough problems, precise enough problems, essentially we win. Our prefactor is huge, so it's going to take a while until we get there. And we're still working on this. This also has to do with efficiency of codes and things like that. But okay, the take-home message from this is that there are ways to actually do Monte Carlo in real time, and that this dynamical sign problem may not be as fundamental as the fermionic sign problem. Okay, we can bypass it to some degree. And I'll tell you that we're now trying to actually apply similar techniques to the fermionic sign problem, but we'll see how far this takes us. I mean, I don't believe it'll solve it in any meaningful way. I believe it could help. I'll say one more thing about this maybe, and that's, I told you about this non-crossing approximation. So what turns out is that you can do this Inchworm and limit the order of Inchworm diagrams that you sum. And if you limit that to first order, then what you get back is the non-crossing approximation. Okay, and that is a very slow and stupid way to perform the non-crossing approximation, but it gives the same result. If you do it to second order, then you get the one-crossing approximation. And that scales better than doing the one-crossing approximation semi-analytically, actually. So that, at least in some cases, for long times, may be better than just doing all the integrals numerically. And then we've done this going up all the way to the 8th crossing approximation. So you know, the computational scaling of these things, okay, going up from non-crossing to one crossing, the cost of that is like n squared, where n is the number of points on your time contour. Okay, so if that's 100, which isn't much, that's 10,000 times more expensive. And that's like going from minutes on a laptop to hours on a cluster. Okay, two crossing approximation. There have been a few calculations of this on supercomputers for very short times. Okay, and we can do 8 crossing approximations and so on. So this is nice because we can actually see the whole thing converge with order. And we can do things that semi-analytically essentially cannot be done. But we also have this nice diagrammatic interpretation. So okay, you can argue about whether this is real or not, but we see that we at least think we have some intuition about self-energies and what they mean, and the order of self-energies and which diagrams go into them. So we can actually have a diagrammatic interpretation of this Monte Carlo process, which gives us a little bit more theoretical intuition sometimes. And in a way that tells us about when it will break down, because it will work as long as your problem is described by a reasonable order self-energy in the expansion that you're using. Okay, so if you can, we can realistically do, we have some algorithms for fast summation of these things. Okay, right, so you have to realize that we lose the determinant structure when we do these Inchworm things. Okay, so we no longer sum up all n factorial diagrams in n to the third time. We have to sum them up one by one. We have a fast algorithm for summing them up in exponential time, which is better than factorial still, but it's costly. So realistically, we can do, I don't know, maybe 10th order, okay, something on that general order. So if something is not described by a 10th order self-consistent self-energy, then we are essentially using the wrong expansion, and this is hopeless. Okay, our method will not be able to describe it. If it is described at very high order self-consistent perturbation theory, which is quite a powerful thing, then we have some hope of capturing it with this method. Okay, so yeah, so this is the Inchworm Monte Carlo. Okay, in my presentation I actually have a video of what an inchworm is. Okay, but it's like this little worm that walks like this, sort of uses its own length to move in a motion called inching, and we thought that was sort of similar to this. So okay, so this is something to look up if you ever really think about. Right, if you need to do Monte Carlo, but you also want to do time propagation. And I think that's it.
Okay, thank you.
Okay, thank you guys.
Are there any questions, Mark? Especially on this cool Inchworm stuff. Yeah. What's limit of time?
Well, so
usually in task.
Well, okay, so essentially the computation, if all of this works and if we remove the sign problem, then this scales quadratically in time. Okay, so in practice we can very easily, like on a laptop or something like that, go to times which are on the order of a few times the inverse dot-bath coupling. Okay, that's the relevant energy scale for hybridization expansion, because it sets the diagram order that you need in order to do it. And if we want to do twice that, then it's 4 times as much computing power. Okay, so if we want to do times 10, we have to use a cluster. If we want to do more than that, we have to use a supercomputer. That's the... Okay, but it's right, I mean, once it's polynomial, then, every year and a half we get an exponential factor, not a linear factor. So this is really... This really sounds like classical physics in a way.